Alright, let's start talking about some real physics here. This is called kinematics. I'm going to go through all of chapter 2 here. So if we split it up in class, you can only watch, you only have to watch the first half or whatever. Okay, so we'll talk about displacement, which is just as you move around, you change position, so you displace yourself a little bit. Talk about the difference between a thing called a vector and a thing called a scalar, and how they relate to coordinate systems. And then we'll talk about regular stuff like speed and velocity and the difference. Talk about how we can look at them on graphs. Then talk about acceleration. Acceleration is the change of velocity. So we start out with displacement, and then we talk about velocity, which is displacement over time, and then we talk about acceleration, which is displacement over time squared. In other words, we're changing our displacement over time, increasing or decreasing our velocity. Okay, and then we talk about the equations for constant acceleration, which is basically free fall, or if you step on the gas and you just start going at a constant acceleration, what's your velocity going to look like? And then some examples of doing one-dimensional problems. So start out with displacement is the main concept we need for studying the topic known as kinematics, and that's just the study of motion without considering its causes. Okay, so when we get to Newton's laws, now we start thinking about forces, but kinematics is just let's just say we already know something's moving. Where is it going to be in the future? What if we do this? What happens? And so on. So your position is described by a coordinate. Displacement is a change in those coordinates, those positions. You start at one place, you walk to another place. So you have x0, or your initial position, and x final, your final position. Your change in position is simply final minus initial. So let's say you started here, and this is 2 meters from your front door, and then you walk to the kitchen, which is 2 meters away. So now you're 4 meters. You do 4 meters minus 2 meters equals 2 meters. So your change in displacement is just 2 meters. Okay, so that's easy. Hopefully, we're just trying to calculate, or actually, we're just trying to learn the notation right now. So we use xf to describe final, x0 to describe your initial position. The difference of them is called delta x, or your change in position, and that we use to describe any sort of change in. So this delta here, anytime you see delta, we're describing a change in something. It could be change in temperature, delta t, change in position, delta x, change in velocity, delta v. Whatever it is, it always means this, the final minus the initial, whatever the quantity is. Okay. For displacement, the unit we use is the meter. So get used to that. 1 meter stick. Sometimes we'll use kilometers or miles. They're just as good. Feet, other things, but you may have to convert them. Okay. Here's an example. Professor pacing around, starts at 1.5 meters, goes to 3.5 meters. So her total displacement during that time is a positive 2 meters. She moved 2 meters to the right. So that would be a positive 2 meters, and that's why we do final minus initial, to just be consistent. So that if she starts at 3.5 and goes to 2.5, then she went negative 2 meters because she went 2 meters to the left, and this way is the negative direction in our coordinate systems that we generally use, where this is x and that's y. Okay, so we've got another example of a guy walking around on a plane, not a big deal. Okay, so distance is the distance traveled, and it's called the magnitude of the displacement. So once we get into 2 dimensions, displacement becomes a vector. So you can imagine if I walk from here to here, I'm in a different spot than if I walk from here to here, or here to here. Okay, so I could walk the same distances, but these displacements are different because you've got 3 people in 3 different spots. So displacement considers your direction, where you went. Distance just considers how long you walked, or what's your distance. So when we talk about distance, we're just talking about the magnitude between 2 points, the total size, not where and when and so on. Okay, so your distance traveled is the total distance between the 2 positions. Okay, there's a misconception here. Make sure you are aware that your displacement and your distance are different, because your direction needs to be considered for example, I could walk, what this is trying to, this misconception, I could walk this way and then turn around and walk back, and where I started, I'm only, let's say I started at 0, I went 2 meters that way, and I went 2 meters this way, so I walked over here and then back, so that means I walked 2, 4, 6 meters, so my total displacement was 6 meters, or sorry, my total distance traveled is 6 meters, but my displacement is only 2 meters because I'm only 2 meters from where I started. So just be aware that sometimes you want to know how far you walked total, and then sometimes you just care about how far away you are from your house. A great example of that is if you walk in a circle around your house, you could walk for miles and never get that far away from home. Alright, so here's an example here. Make sure you work through that. Vectors, scalars, and coordinate systems. So I was alluding to this a little bit ago. Your displacement is generally a vector. Not generally, your displacement is a vector. The magnitude of the displacement is the distance you traveled, not the total distance you traveled, but the length of that vector. So when we talk about vectors, it contains both magnitude and direction in it. Okay, so it has to, if you start at this point and you want to go here, you're going to want to walk this way. North, if this is north and this is east, then you want to walk northeast and get there. So you care about which direction you're traveling. If you want to go to Des Moines, you want to head west. If you want to go to Chicago, you want to head east. So you want to make sure to consider your direction when you're talking about a vector. Usually in one dimension, you have two options for your directions, plus or minus. So if I'm only allowed to move back and forth in the positive or the negative direction, I can go this way and end up there, or go back this way and end up there, and so on. Okay. So a different thing is called a scalar, and a scalar is something that has magnitude but no direction. For example, temperature. Whatever the temperature is, it's not moving around. You don't have to consider whether or not it's changing. Generally, the temperature is just 20 degrees or 18 degrees Celsius or 22 degrees, whatever it is. It's a little bit tricky here to talk about the difference between a vector and a scalar, but you'll start to see the differences between them. But a vector is anything that has magnitude and direction, like a force, like your velocity, or like your displacement. But a scalar is anything that is just a number, like how much money you have in your bank account, or how many grains of rice are in a thing. Okay, just a number. There's no direction associated with it. So coordinate systems, for one-dimensional motion, generally you just have one dimension here, plus x and minus x, and objects can go back and forth and move along that line, and it's easy. You just use rate times time as distance. This is like when you're driving on a highway, you're really only doing one-dimensional calculations. If you're trying to estimate how long it will take you to drive somewhere, you're doing a 1D kinematics problem. And we'll get into 2 dimensions and later, and I don't think we'll get into 3 dimensions, but it's not too much harder to add a 3rd dimension. It just gets a little more tedious, so that's why we stop at 2. Alright, so time, velocity, and speed. Time is a scalar. Okay, time is just 1, 2, 3, and so on, and the unit of time is seconds. The elapsed time is just like, so there's your delta t again. I said earlier delta t for temperature, that would be a capital T. Delta lowercase t is time. And you do the same thing. Let's say you start at 11 a.m. and end at 50 a.m. That's a 50-minute difference. So your elapsed time would be 11:50 minus 11, so you'd have 50 minutes of delta t there. Okay, so you do the same thing. So if you want to calculate your velocity, you just do delta x over delta t, or your change in displacement over change in time. So that's going to be x final minus x initial all over t final minus t initial. And that's how you calculate your velocity. So there's your average velocity here. It's your final position minus your initial position divided by the time it took when you hit your stopwatch at the end minus the time when you started. Okay, and that is defined as your average velocity. When we put a little bar over top your variable, that means average. So you can see there's a little bar there on the top of this. that is signifying average velocity. Okay, so you know, if you, that plane example earlier, if he walked 4 meters, but then he did it in 5 seconds, then his velocity's average velocity would have been 0.8 meters per second. He could have walked the first half quickly and slowed down the second half. What you care about there, you'd want to measure it more discretely with shorter time intervals. But if you all you had was your initial and final positions and initial and final times, you can only calculate the average of the velocity. But that minus sign means that the passenger walked on average 0.8 meters per second to the left in the negative x direction, okay, in our coordinate system. Same idea. So if you make your time intervals shorter and shorter, then you can get your instantaneous velocity, which would be the velocity at the moment that you measure it. You have to make the time intervals and the displacement intervals very short, but if you do it a bunch of times, you get a very precise reading, and that's how your a police car, when it's measuring you with a laser beam, sampling your velocity very quickly, your change in position over change in time many times a second, gets a very nice approximation of your instantaneous velocity. Okay, so there are two important things, speed and velocity. Velocity is a vector, speed is a scalar. Now you're gonna go, what the heck, dude? What are you talking about? Well, velocity, when we talk about velocity, sometimes we care about the direction you're heading, sometimes we only care about how fast you're going. Okay, the difference between velocity and speed is that velocity is has the direction encoded with it. So I could say plus 3 meters per second, and that might mean I'm moving to the right at 3 meters per second. If I just said 3 meters per second, that just means I'm moving 3 meters per second. You don't know which direction I'm moving. You obviously don't care because you didn't ask for that. You just wanted my magnitude, okay? And we could write that with absolute value signs. That often indicates a magnitude. So this would be the same as just writing 3 meters per second if you put these around a vector. That just means tell me the magnitude, and that's what that implies. Okay, so that's your difference. Make sure you know the difference between speed and velocity. Okay, they could be the same thing, they're just displacement over time or change in position over time, but you do it where you ignore the actual direction. Okay, there's a couple examples here. All right, so here's some graphs, and this would be let's say, there we go. Okay, so let's say you start at home. So your position is 0 kilometers from where you're starting from. And then you start driving. And you drive for half an hour, it looks like. Okay? And in half an hour, you drove at a constant speed, looks like, to 3 meters. Why is it a constant speed? Because your slope is constant here. Your rate of change of position over time is constant. It's a straight line. So that means your velocity is constant. So you drove for 20 minutes or so, 25 minutes at a constant speed, stopped, turned around, and drove back home. Why? I don't know. I don't know why we'd do that. Maybe you got to this street, realized you forgot your wallet, turned around, came back home. Okay? Same speed, but in the negative direction. This is your position versus time. This is what the velocity versus time looks like that whole time. Okay? Your velocity versus time is constant. For that first 25 minutes, you were driving at, looks like 12 kilometers per hour until, boom, you turned around, and now you're driving back home negative 12 kilometers per hour. So there's this point where it switches really fast because you turn around really quick. You go from a positive velocity to a negative velocity because you're driving, and then you turn around, and now you're going back the other direction. So this would be the same thing as driving, turning around, coming back, okay? And from here to here, since you have a constant velocity, then you're going to be increasing. Every one of these is adding distance, okay? Adding distance until it gets up to here, okay? And that's what this area under the curve, the area here is equal to this point up here. Tells you how far you're going to travel at the end of that, okay? So if you look at this, it's about 12 times about 0.25 or so, and yep, multiply those. Okay, so 12 divided by 4 right? 0.25 is a quarter, 12 divided by 4 is 3, and there's 3 here. So the peak of this point is 3. 12 times 0.25 gives you the area here, and that area by the end of that velocity is your highest point there. Okay, your speed, look at this. Your velocity was the same, you turned around, you went the same velocity, so your speed is going to be the same 12 meters or kilometers per hour that whole time, because your speed is a scalar and not a vector, so it doesn't go positive and negative, you just went the same speed the whole time. Okay, so that's just an example of the difference between a scalar and a vector. Okay, so finally we have acceleration, which is the same thing as position and velocity. Not the same thing, what am I saying? Velocity is change in position over change in time. Acceleration is now a change in velocity over time. So if we go back to this graph, this is constant velocity. If our velocity was changing instead of being a straight line, then we would have a non-zero acceleration. In both these things, if I were to draw a graph of acceleration versus time, okay, the graph would be 0 the whole time, okay, because the velocity is constant. So the rate of change of velocity, 12, 12. So 12 minus 12 over that delta t is 0. Okay, 12 minus 12 is 0. All right, so your average acceleration is the rate at which velocity changes. And so you just put in your final velocity minus your initial velocity and divide by their change in time, like normal. Acceleration is a vector because, again, since velocity is a vector, obviously acceleration is, since it uses velocity in its calculation. But if you accelerate in one direction, you could, which is my favorite band, by the way, you could speed up. If you accelerate in the other direction, you'll slow down. Slowing down is called deceleration, but it is acceleration with a negative magnitude. Well, not a negative magnitude, but a negative direction. Okay, so here's a misconception alert. Okay, deceleration always refers to acceleration in the opposite direction of the velocity. Deceleration always reduces speed, but you could have negative acceleration, which is just acceleration in the negative direction, which is dependent on your coordinate system. So just, if your car is going this way or that way, just make sure you understand if you're speeding up or slowing down. Okay, so this is a really important thing. You need to decouple in your brain the velocity vector and the acceleration vector, okay, because you could be, in this case, the car is moving forward but decelerating, so that just means that this arrow is going to get shorter and shorter and shorter as he slows down because your velocity is going to get lower. So your velocity and your acceleration can be in different directions, okay, so just make sure you understand that. Down here, same thing. B and C are the exact same case. You would just be on the other side of the street watching it happen, for example. And then A and D are the same as well. Okay. Okay, yeah, so work through that example, just talk about that. Instantaneous acceleration, same thing. If you measure your change in velocity over change in time over a very short period, you can get a very nice measurement of your change in acceleration. Then there's more examples here calculating those. Calculate displacement, bunch of examples here, work through those. Here's a little more complicated set. You're going to see these three graphs all the time. Position, velocity, acceleration. Okay, position over time. Look at this. This is not a straight line anymore. That looks more like a exponential. It looks like, actually it looks like we're accelerating here, and then we have a constant velocity because that line is straight, and then we decelerate here because we slow down. So what am I looking at? I'm looking at the change in position over time, and we're quickly changing position, and then we change position at a straight line rate, and then we quickly change our position in the negative direction. So to me, that looks like we accelerate, slow down, actually accelerate, maintain constant speed, and then decelerate. Okay, so make sure you understand that when I talk about that. Our velocity versus time graph here, if we look at this, in this case, we're accelerating, right? I can tell because that looks like a x squared, looks like a parabola, looks like a whoop. It's got a little bit of an exponential curve there. It's not a straight line. That means our velocity versus time is not constant. It means our velocity versus time is increasing. Look at that. And there it is. From there to there, okay, from there to there, we have acceleration. And then our velocity versus time is flat. Boom. There's a flat line. See that? Okay, flat line, straight line, and those are linked. Those two things are linked. And then look at this, our velocity slows down. Okay, we go from 8 meters per second to 0 meters per second over a short time interval, which means we decelerate. And there it is. So what is our acceleration versus time going to look like? Well, we have non-zero acceleration here, and this area under this curve here tells us our maximum velocity at the end of it, because you're adding up velocity plus velocity plus velocity. Okay, so if I do this again, 0.4 plus 0.4 plus 0.4 plus 0.4 plus 0. We're adding all that up for each of these time intervals, and every time you do that, boop, 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 you speed up, you increase your speed. Okay, so then that area there gives you that, and then since we're not changing our velocity at all here, then we have zero acceleration. Our final velocity minus our initial velocity, 8 minus 8 over that delta t, is 0. And then we do the same thing here. We have negative acceleration because we're slowing down. Okay, so if we look at these three graphs and then compare those special spots, I'm trying to, okay, where we have acceleration, no acceleration, and so acceleration greater than 0, acceleration equal to 0, acceleration less than 0, because we are increasing our speed. So we have positive acceleration, change in velocity is positive slope, and our change in position is curved. And then we have constant speed here, because our change in position is constant, it's constantly increasing. Our velocity is constant during that time, which means we have zero acceleration. Our curve here, we're slowing down, and we have negative acceleration. Okay, so make sure you can link those three things together in your head. Make sure you understand what these three graphs are saying and why they're related to each other. Okay, very, very cool stuff. And we'll talk about the equations that make these lines happen. Okay, x is 1/2 at squared, v is at, and then a is a constant. Okay, a equals some constant during this time interval. Velocity is acceleration times time. Remember, what is acceleration times time? It's acceleration, the y-axis, times time. That's the area of this curve, because area is height times width, or length times width, or whatever. Okay, and then this shape here is a parabola, 1/2 at squared. Okay, acceleration is our constant. Acceleration is our constant during that time. There's our three equations that govern these things, and they're all related. Okay, all right. Now we go, there's more examples here. Okay, so the motion equations for constant acceleration in one dimension. Kind of working through them here. Yeah, they're just going through the equations. Okay, so these are the, let's see, they have those equations there. Let me just make sure I found the right ones. Okay, so to get our first two new equations, we start with the definition of average velocity. Velocity is change in position over change in time. Solve for position by putting in your x and x0, and then leaving t as your total elapsed time, and you get this equation here. X is x0 plus vt. This is nothing more than rate times time, vt. Rate times time equals distance. That's what this equation is. So this is with if you have no acceleration, okay, then you have rate times time equals distance. Okay. Moving on, there's our equation again. Rate times time equals distance, and then x0 is wherever you started. Could be 0, could be 10, whatever. You're just adding vt to it. All right. And there's some examples there. So there's your line, and then acceleration is velocity over t. Do the same thing. There's our v is v0 plus at. So our velocity at any point, if we have constant acceleration, is just at plus our initial velocity. If you accelerate for this amount at that rate over this amount of time, that gives you velocity. You can add that to your initial velocity, and then you end up with more velocity. Okay, so there's some examples there. Then you put these two equations together, and you get this beautiful thing. X is x0 plus v0t plus 1/2 at squared. Okay, there's your full equation that's your kinematics equation for everything. It looks scary, it's not. X is x0. Where did you start? Did you start at 0? Most of the time you will, so you can ignore that one. Otherwise, it might be I started at 10 meters and then I hit the accelerator, and where am I now? And that will tell you where it will be. You will add velocity times time. Okay, if you're moving at some initial velocity, that initial velocity will continue to increase your distance. So of course it's going to add to your initial displacement, and you'll continue to increase your distance. Plus 1/2 at squared. Okay, so if you do 1/2 at squared, you have constant acceleration over this amount of time, then you get a parabola. You get a exponential looking curve, okay? And there is your full kinematics equation for things. If you have no initial velocity, if your initial position is 0 or your initial velocity is 0, then your position at any time is just given by 1/2 at squared. So it becomes a pretty simple equation. 1/2 times your acceleration, and then just squared the time. Okay, so that's it. That's your first big kinematics equations. So here you go. There's a dragster's 26 meters per second squared of acceleration, and say a dragster does that from rest for 5.56 seconds. How far will it travel in that time? Okay, so we got a dragster starting at some initial position. Where's its final position going to be? And we're going to accelerate at a rate of 26 meters per second squared. Okay, so our initial position we can make to 0. We're starting at rest, so our initial velocity goes to 0. So boom, boom, our equation simplifies just to x equals 1/2 at squared. Okay, x equals 1/2 at squared. 1/2, our acceleration is 26 meters per second squared. Our time is 5.56 seconds squared. Multiply all that together. We travel a distance of 402 meters in that distance, about 1/4 of a mile. All right, so again, look at this. We plugged in these numbers, but we did not leave the units off. The units always go with the numbers. So we have, for acceleration, meters per second squared, and then we multiply by time, which has units of seconds, but it's t squared, so it's second squared. And you see the second squareds cancel out, and the unit that we have left is meters. Okay, and the distance we travel is meter. And then you do the same thing here. There's a couple other equations. Here's another one. You just solve for by doing some substitutions. So in this equation, we have v squared equals v0 squared plus 2ax. Notice this equation, we got rid of time. So sometimes we can ask you a question where you don't know the time, and you don't need to, because we canceled it out. Okay, it's no longer in our equations. So here are all of the kinematics equations. Rate times time is distance. Average velocity is there. Velocity is this. X is 1/2 at squared, and v squared equals v0 squared plus 2ax. Okay, what you can see is this one has no time variable in it. This one has no final velocity variable in it. This one has no x variable in it. So these three kinematics equations here can be used to solve for any situation, even if you don't know one of the variables. So you'll use each of those equations separately. Excuse me. Okay, some more examples. You should work through those with your friends. Makes it easier. And then some problem-solving techniques. Determine the principles involved. Really helps if you draw a sketch of what's going on. Okay, what direction are things accelerating? How long are they? What's your initial velocity, and so on. Make a list is what is given. So you could say x0 equals, is it 0? V0, is it 0? V final, is it 0? Could be 0. You could be starting from some number. So you write your x0, v0, vf, v t final, t0, a0, a final, or if you, it's just actually you just have acceleration. It could be 0, it could be something else. Write down all your things, and then just go to the equation. Figure out which one you do pattern recognition and match the equation that has the variables you need in it and the one you don't, and then solve for it. And there you go. Find your equation that can help you solve the problem. All right. So Here's your other thing. Make sure you do your unit conversions properly. Okay, falling objects are great because when you drop something, they accelerate every time at 9.8 meters per second squared. Every time. That's the acceleration of gravity. It varies slightly depending on where you are on Earth, because sometimes Earth has a little bit more gravity in certain places. If you move further away from the center of the Earth, or if there's more rocks where you're at, could have a slightly higher, I mean, the density of Earth is higher, you could have more gravity in that local area. So then your free fall equations, acceleration becomes g, which is 9.8 meters per second squared, and you just replace a with g, and then you get your three equations again, this one with no x, this one with no final velocity, this one with no time, and you can solve for each of those things. We replace x with y because we're talking about moving in the y direction, but the equations are the same, whether you're free falling or accelerating in a car. Then there's some examples here of calculating the different problems. If you throw something up in the air, goes up and comes down, follows a parabola because it's undergoing constant acceleration that whole time. Constant acceleration, negative 9.8 meters per second squared, which means your velocity is constantly decreasing, even going negative, which means your initial position. So make sure you understand how you could be going in a positive direction, only finally getting in the negative position, whereas your velocity is positive until 0 and then comes back down. Notice the peak should correspond, it's not really great lineup of the graphs here, but your peak position should correspond to this point where it crosses there we go. Your very topmost position corresponds to where your velocity goes from positive to negative, where it crosses 0. Because when you toss something up in the air, it pauses for a moment where it reaches 0 velocity. Okay, so here's your example here. You throw something up in the air with an initial velocity. It's going to decelerate at 9.8 meters per second squared during that whole time, and you're able to calculate where it would be at any point. If you drop something, here's an example. Right? It accelerates, it speeds up as it falls, so it's not a straight line. Constant acceleration, velocity is changing as a function of time. V equals at, slope of that line is acceleration, y equals mx plus b, so a and m are linked in this graph, and then this is x equals 1/2 gt squared. That parabola gives you that shape. Okay, so there's more examples here. Okay, graphical analysis, your one-dimensional motion. Remember, if you have a line, the slope of that line, or the steepness, is called the rise over run, or the change in y over change in x. That tells you how quickly the line is increasing or decreasing. And it's really nice. You can relate this to your equations, or keep them separate in your head if you want, but it's nice to see that what this is saying is your position, which is the y-axis, at any given time is equal to your initial position, which is x0, which is called the y-intercept, or the moment it crosses. What is the value of x at t equals 0? That's what your y-intercept is. V is your slope, your rate of change of position, and t is the time elapsed. So if you multiply t times v, it should bring you up to wherever you need to go on that graph. Okay, so that's what this is trying to tell you, is relate these equations to these pictures. Okay, spend some time and think about that. It really is cool. Okay, same thing here. We've got, in this case, constant acceleration. So what we did here with our position versus time is going to apply to our velocity versus time, because now we have constant acceleration. In this picture, if it's position versus time and it's a line, that means we have no acceleration, constant velocity. When we have this, we have constant acceleration, and then our velocity is changing. So then our position versus time is going to be more accelerating, look like a parabola. Okay, so yeah, and then here's just some generic graphs for more general things. Okay, that's it. See you guys later.